Alrighty, we are doing table I, which is so much easier than potential energy diagrams. You're going to be in love. So table I is all about reading and manipulating equations. Table I has a bunch of equations that can be read both forwards and backwards on it, and all of them come from potential energy diagrams. So table I shows heat of reactions for multiple chemical reactions, and you should remember, I just told you should remember that a negative delta H is an exothermic reaction, and that is when energy is released or when energy is exiting. Remember, exo, exiting. And a positive delta H would be an endothermic reaction where energy is being absorbed or it is entering. Now, table I is a New York State reference table. You can find it online. You just Google New York State reference table. There, I believe, are 20 equations on there. Most of them can be read forwards and backwards. Some of them are dissolving in water. Those are the ones with the arrow and it says H2O over the top. There are some where it is synthesis of a compound. Some of it is synthesis from its elements, it likes to say. But we can manipulate these equations very easily. You can manipulate any equation, really. It's just table I has 20 of them that they most commonly use on the Regents exam. So the delta H given is for the reaction as it's written from left to right. Same way we always read. And if you want to flip the reaction and do it backwards, say table I gives you a synthesis and instead you want to do a decomposition, you would take the reaction and flip it. And when you do that, you would have to change the sign for delta H. You're doing it backwards. So let me see if I can move this little bubble. See, it's moving much easier now. Move this way. Oh, come on. Come on. There we go. All right. So you can see here that we have a synthesis right here. We have nitrogen and hydrogen. We have to break bonds and then we have to form new bonds. So it's a combination of breaking and forming. And overall, that would give us an exothermic reaction of, someone's at the door, of negative 91.8 kilojoules. But if I wanted to take that same reaction and instead of making it a synthesis, make it a decomposition like this down here, I just flip the sign of delta H. It's that easy. Now, did I skip something? No. Okay, so there are times where I want to double my reaction. If you remember back from mole ratios, we talked about doubling a recipe or tripling a recipe. Same thing happens here. So if you want to take a synthesis reaction, and in this case, you're making 2 moles of ammonia, instead of making 2, you want to make 4, it takes double the amount of energy. So you would take your original delta H and you would double it because you've doubled the reaction. Double the amount of stuff, you need double the amount of energy. Next, you can do the same thing if you want to half the reaction. Usually we don't like for our coefficients in... there we go. We don't like for our coefficients to be fractions or have decimals in them. That's really frowned upon. We really like the simplest whole number ratio, but sometimes you just need it for the numbers or more so in a lab setting. But if I wanted to make half the amount of ammonia, instead of making 2 moles, I want to make just 1. Remember, there's an imaginary 1 right there. I would take my delta H and cut it in half. So I went from almost 92 to almost 46. And next, where does this come from? Every reaction has different atoms with different electronegativities, different types of bonds, different atomic radii. And for that reason, when we break bonds or when we form bonds, we are exchanging different amounts of energy. And that's why all of these have different numbers. Every exothermic potential energy diagram is not the same. The only thing that's the same about them is that overall you have a release of energy, but you can have a release of a tiny bit of energy or a release of a lot of energy. Any which way, that would be exothermic. So all of these particular reactions were calculated. They have potential energy diagrams, each with their own different sizes. And again, you should remember that delta H is equal to the potential energy of your products minus the potential energy of your reactants. And that is all I have for you. Table I is much simpler than potential energy diagrams. If you didn't catch anything, rewatch the video. Watch it again. Watch it again. I'm pretty sure I've only been at this for like 4 minutes. So, if you rewatched it already and you still don't get it, leave me a comment and I will do my best to help you. Thanks. Bye.